Start with regression. Okay, regression is the most fundamental learning approach. And in a sense, we've already done regression. If you think about maximum likelihood estimation, that's some sort of a regression, right? You had some data, and effectively, you learned your parameters to fit the data. So in a sense, we've already done learning. But the lens through which we will look at this would be a little different. Okay, so let's maybe just do least squares regression, take a break, and then we can wrap up. Okay, so we'll start with least squares regression. And effectively, what you're trying to do is you have this problem, Ax equal to y. So this is an m by n matrix. So you have n by n, n by 1, m by 1. Okay. And if m equal to n and a is invertible, well, that's your high school problem. But generally, like and you've already seen this, right? In the maximum likelihood estimation, what was a in your maximum likelihood estimation that you did?
G.
Yeah, G. So does it have more rows or more columns?
More rows.
More rows, right? So it basically looks something like this. One application of least squares regression, of course, is this is your data. These are your model parameters, and this is your state matrix or something, whatever. Right. So let's first consider the case where m is greater than or equal to n, and a has full rank. Full rank meaning the rank of, in this particular case, rank of a is m. Okay, so what does least squares regression do? It just says, I want to minimize the 2 norm of the difference between the data and the model prediction. So y minus ax transpose y minus ax. I want to minimize this over x, right? So this is least squares minimization. So first we'll do this assuming it's just an ax equal to y problem. And then in the next lecture, we'll view this from the lens of statistical learning theory. Right? What can we say about confidence, predictions, probabilities, and things like that. Okay, so this should be an easy problem to solve. Let's just expand that. So this is minimizing over x, y transpose y, minus x transpose a transpose y, minus y transpose ax plus x transpose a transpose a x. And this is nothing but anyway, first of all, this term can be ignored, right, because it has nothing to do with x. And what can you say about these two terms? Sorry?
They're transposes.
Yeah, they are transposes of each other. Can you say something else?
Write AX as y.
Sorry?
Write AX as y.
Yeah, they are the same because this is a scalar, right? This is a 1 by n, so this is a 1 by 1 matrix. This is a 1 by 1 matrix. So this is just a scalar. So this is the same as minimizing two x trans, minus 2 y transpose ax plus x transpose ax. Okay. Because this is just these are 1 by 1 matrices. And now you can differentiate it. And the solution to the solution to this problem, basically setting that, or first order conditions, basically give you x hat equal to A transpose A inverse A transpose Y. Okay. So this is the least squares solution. This is the least squares approach to solving Ax equal to Y. Okay, we've assumed full rank, which means this is invertible. Okay, so that's the least squares, so it should be fairly straightforward, right? So what can we say about the least squares solution? I'm going to well, this is almost like, this is the difference between inference and learning. I didn't think about it that way. So this is where your inference ends, right? You've estimated your parameter, you're done. In learning, it matters what you do with it, okay? So call this equation 4 or something like that. I want to multiply equation 4 by A. So you have Ax hat is A transpose A inverse A transpose Y. Okay. Or Ax hat minus A transpose A inverse A transpose Y equal to 0. So this equation is a bit profound. So what does this tell us? What does this equation tell you?
The error.
Sorry?
The error.
The error?
Between like your predicted value.
Well, the error, I mean, how do you define error?
Okay, never mind, it's equal to 0. So.
Sorry?
Never mind, it's equal to 0. So.
Yeah. So if you had, say, I mean, in a sense, this is an error. But in what sense okay, I take it it's an error, but in what sense? I would use a better word than error. I think you're, I would call it a residual.
Okay.
Okay. In what sense is it a residual? So this matrix you would have seen before, right? So what is this matrix? From your linear algebra class, what is that matrix? Or if you given any matrix A and a vector Y, when you apply this matrix to the vector, what does it represent?
So projection.
It is 100% a projection. So if you have some, let's say you're in some space, say 3-dimensional space, and you have a point in that space, and then you have a matrix. Think of a matrix as representing, a basis. Okay, so this is basically the orthogonal projection projector with span being, okay, the simplest way to think about it is if you consider the columns of A to be basis functions, then this A times A transpose A inverse A transpose applied to Y basically projects Y orthogonally with respect to the basis. Okay, so let's look at this graphically. So now we are looking, this is the space of Y, okay, or the output space. And let's say this is Y, this is your particular Y, and this is range of A. Okay, so this line is range of A. So what does range of A mean? It's been a while since you had linear algebra. What does range of A mean? Yeah.
It's all possible vectors that you can get by multiplying any vector x.
Yeah, exactly. So if you take all possible x's in the world and you multiply those x's by A, all those x's will fall on this line. That's the range of A. Okay?
I mean, but I thought we took A to be full rank, right?
Yes, you're full rank, but you're not a square matrix. You're rank M.
Aren't we rank n?
So, which is the smaller one? Yeah, you're rank N, sorry. You're rank N, and Y lives in M-dimensional space. Okay? So let's call this Y1, Y2. Let's say in this particular case, Y is 2-dimensional, X is 1-dimensional. X lives in 1D space. So AX would just be a line. Right? In your ballistics problem, Y was 9-dimensional and X was 3-dimensional. Right? So it's a hyperplane. Okay? So now you have this plot here and you have this equation here. What does it tell you?
The x star lies on that line which is orthogonal to.
Exactly. So what it says, it's very beautiful, right? One of those things we should appreciate. So this is what it says. This is x hat. So what this says is the least square solution is nothing but you have a point, this is your data y, you project that y onto the range of A, and x hat is the closest point to y, or ax hat, okay. Ax hat is the closest point to y.
It's basically a Gram-Smith, no? Like the Gram-Smith theorem that you try to orthogonalize a set of vectors.
Yeah, that is orthogonalization. But yeah, this is yeah. So anyway, what this tells you is ideally your ax should be equal to y. Ideally your ax hat should be equal to y, right? Then you're done. That's the problem you're trying to solve. But the best you can do is, but you're completely constrained to be on this line. So the best you can do is basically be to minimize the error. So you get the minimum error between, another way to think about it is A or, okay, let's find it. And the way to think about it is AX hat is orthogonal to range of A. Another way of saying that is like your words. This is the minimum residual you can have, right? Again, if AX hat was equal to Y, then there is no error, no residual. But basically, least squares gives you the minimum distance between Y and the best model you can have. The best model.
Write that as the difference.
Sorry?
Y minus.
Yeah, you can show that Y minus AX hat transpose AX would be equal to 0. You can show that. But that particular thing is basically showing the difference between.
That won't be a regular product, though. That should be an inner.
This would be an inner product, yeah. Okay, so anyway, what least squares gives you is the minimum distance. And now let's take a break, come back and do least norm, which is the next, which is the overdetermined case. This is the underdetermined case.
Would this hold for any x?
Sorry?
The y minus ax hat transpose.
Yes, that will hold for any x. Let's test that hypothesis. So y minus a, what is the expression for x hat? A transpose A inverse A transpose, right, is x hat, right? Y.
It would only work if you have like really flat space, no?
Should be a difference.
Sorry?
It would only work if you have a really
Oh, everything is linear, everything is a flat
Yeah.
space. Yeah.
But then you would need enough data, no?
No. Any amount of data you have, this is the best you can do.
Yeah, but if the reality is curved, and then you're assuming that you're in the tangent plane all the time, you need a lot of data, no?
You're assuming A is linear. This is all in the Euclidean space for now. Yeah, there are equivalents when you have curvilinear spaces.
Wait, for that boxed statement, should it be y minus ax? Is
Sorry?
for the boxed statement, should it be y minus ax hat is orthogonal to the range of A?
Yeah.
The boxed statement, because it just says.
Oh yeah, y minus ax hat, sorry. Okay, so yeah, let's do this now. So now this is y transpose minus y transpose A transpose A inverse A transpose. Have I got all the A's? Okay.
No, the A transpose A inverse also needs to be transposed.
So A transpose A inverse transpose will just be the same. It's a symmetric matrix. Okay, so here is your, this thing is gone, this thing is gone, right? Are you convinced now?
I feel like it should be AX difference, but
Sorry?
but it should hold for AX minus AX1 minus X2 for any X1, X2.
Sorry, what?
Instead of AX, it should be AX1 minus X2.
No, we just proved it here, right? So this is any X. Okay? So, I mean, all I've done is, okay, so this is y minus ax hat times ax. So this is orthogonal to this. I've just substituted the expression for x hat, and I've just done the transpose, right? So this is rock solid. There is nothing. But yeah, if you have something that's not sitting right, well, we are in the break, so we can take advantage of the break.
I mean, first, it should be an inner product, so it being a direct product of matrices feels wrong.
Why is it wrong? Because this is a vector, and the transpose of a vector times a vector is just a scalar. See, A is a matrix, but X is a vector and Y is a vector. So this is just a vector transpose times vector.
Okay, okay.
But good to think at that level of granularity. How long of a break did we have? If we had a break.
6 minutes.
Okay, so we should get started. All right, so yeah, any questions? Should be very straightforward, right? So this is a linear problem. You basically are minimizing the 2 norm of y minus ax, right? So this is nothing but the square of the 2 norm of y minus ax is being minimized with respect to x. And this is your minimizer. And what we're able to show is, this is all possible ax's lie along this line. So the least squares just picks the one that is closest in the sense of an orthogonal projection. So the least squares is an orthogonal projection. And this is the residual. So this is y minus ax hat, and this is the range of A.
Karthik,
Yeah.
maybe the question is really jumping,
Yeah.
but your paper on the pressure that you did, do you think there is some kind of interpretation through this?
Oh yeah, that's a different projection. Yeah, it's a different kind of projection. Yeah. Okay. All right. So now let's do the other problem. So now we have ax equal to y, m by n, n by 1, m by 1, except in this case you have more parameters than observations. So the previous case was underdetermined. And this one is obviously overdetermined.
Is it not the other way around?
Yeah.
Overdetermined, underdetermined, yeah. it's underdetermined in the sense that you have more equations than unknowns, right?
More unknown.
The
More- sorry.
More.
unknowns than equations. Should be over.
More.
Yeah, wait. Yeah, you have more unknowns than equations. Yeah, that's right. I don't know why I'm binary. My binary is bad today. You have more unknowns than equations, which means you will not get a unique solution, right? The least squares was unique, right? It was, or at least the solution to the least squares problem, you had at least a chance of getting a unique thing. Whereas here, many choices are possible. Many combinations will give you the same answer. So you can post this in the following form. Okay, so this is called the least norm problem, least norm minimization. What the least norm minimization says is minimize x transpose x such that ax equal to y. Okay. So in the previous case, ax, I mean, unless you had precisely enough data and the right amount of data, you would never get to ax equal to y. But here we know that we can satisfy ax equal to y, but I want to satisfy it. I want to find those vectors x that give me, that minimize this. Okay, so now you're adding some additional constraints so that you can actually get a unique solution. Otherwise, you won't get a unique solution because many possible x's can satisfy this equation, right? And you would basically write it as a Lagrange. So you basically say this is same as minimizing x transpose x plus some lambda transpose, let's say y minus ax. The transpose and ellipsize just to make sure you're keeping these straight. Right? You find me the x that minimizes this, right? So this is your objective and this is your constraint. And just 2 or 3 steps of linear algebra, which I'll skip. The solution to this problem is x is A transpose inverse y. And again, here we've assumed A has full rank. If A does not have full rank, then A transpose inverse, you cannot do that. You cannot directly invert. But that's okay. Whenever you cannot invert, you can use, if it's not invertible, what would you use?
Pseudo.
Yeah, pseudo inverse or the SVD, right? You can do an SVD of A and take the inverse of the SVD. But let's worry about that later. So this is the least norm solution, right? So the least norm solution, there are many possible x's that can satisfy ax equal to y. I want to pick the x transpose. I want to pick the x that is minimum in magnitude. So just like we had a very interesting, so what did we have previously? We had something like y minus ax hat transpose ax equal to 0, right? Which means, so this is the residual and this is the range of, so this was least squares, right? So just like we had that property in least squares, in least norm we have another interesting property. X minus x tilde transpose x tilde equal to 0. Okay, so this is what least norm solutions satisfy. So what does this mean? Well, we got a good interpretation of what this meant, right? What this meant was, if this is y, and this is the range of x, this was basically ax hat. So you were pretty much orthogonal to the range of ax. What does this tell you?
Karthik,
Yeah.
I have a question. For the why you want to minimize the x transpose x and not just identity minus that?
Okay, so that's a good question. We'll get to that as soon as we see this.
Oh yeah,
We'll get to that right away. But the answer to that will be illuminated by this.
Yeah.
So always, right, let's go graphical, right? You want to think of in some kind of graphical space. So now there is a difference. Now you are in X space. I hope I wrote, yeah, so this is the space of Y. So this is, now you are in the space of X, the input space. And you could have, okay, so here is a manifold. So along this line, basically Ax equal to Y. So along this line live solutions to Ax equal to Y. And what the least norm picks is basically this is what the least norm picks. So all of these x's along this line satisfy Ax equal to Y. Again, here think about x being two-dimensional and y being one-dimensional. So along this line, all valid solutions of Ax equal to Y live. Okay, now think of it in space of PDEs, right? Along this manifold, all your Navier-Stokes solutions, all your your momentum equations are valid here, but maybe continuity is only valid there. Think about it that way.
And then pressure projects you to the right solution.
Yeah, exactly. So anyway, let's not talk Navier-Stokes just yet. But anyway, so what least norm gives you is effectively, here y is projected to the range of A. Here you're basically projecting x to the null space of Ax minus y. Okay, but anyway, we can spend some more time talking linear algebra. But I think the main point is this is all possible solutions. You're choosing the solution that is basically closest to the origin, right? And like what you were asking, nobody's stopping you from saying, do minimum of x minus x naught transpose x minus x naught subject to Ax equal to y, right? If you do this, then instead of finding the point on Ax equal to y that is closest to the origin, it'll find a point that is closest to, I don't know, if this was your x naught, it'll find a point closest to x. But yeah, think about it in a Bayesian or regularized inference setting. X naught is your prior, and you're moving the least from your prior while satisfying your constraints. That's precisely what is happening.
And you take the KL and you put Gaussian, it's that.
Yeah, it'll be the same. If everything is linear, KL, Gaussian, then it will be the same thing. You'll get exactly the same thing.
So that statements for x's that lie on the x.
Sorry, what?
The statement we wrote is for x's that lie on the x, not for.
Yeah, not for any x, yeah. See, all the other x's can lie anywhere in that plane, okay? Only on that linear manifold, in this case a line, is where valid solutions to ax equal to y lie. And then you're picking least normal, basically pick the one that is closest to the origin, or in this case, the closest to x naught, in an orthogonal sense. Okay? All right, and just like, it's almost like, it's not by design, but sort of by design also. Like, towards the end of the lecture, we'll start looking at plots and stuff. But are there any questions on this? Right, when you had more equations than parameters, you do least squares, and when you have more parameters than equations, you can do least norm. And both of these have this nice property, so this is how you think. And again, it doesn't look like there are any linear algebra pilled people here. Yeah, so this is like a projection to the null space of Ax minus, a null space of A actually. But whereas that's to the range of A. Okay, so now let's do some interesting things here. So what have you seen so far? Sorry, was that a question? So far, one way or the other, we're doing, okay, let's just take the least squares regression case, right? So we said, I want to do Ax minus y, I want to find an x that satisfies Ax minus, that minimizes Ax, the square of the 2 norm. Then you can ask, why the 2 norm? Why not some other norm? What is the answer to that question typically? What? Yeah, okay, you could say this is somewhat smooth.
Euclidean distance.
Euclidean, maybe, yeah. But it doesn't, you can use it for non-smooth, other things, and non-Euclidean also you can use this. But there is something more fundamental. So, I would say something more practical.
Does the square correspond to the Gaussian square?
Yeah, the connection to the Gaussian is there. Yeah, so this is basically pretty much minimizing this is like maximizing the likelihood, right, in the linear Gaussian case. But that's not a reason. It's actually somewhat cheesy question. It's actually real. Why not some other norm? I mean, you all, yeah.
What I was always told is that it's positive, and so if you take an L1 norm with just a straight residual, add them up, it could seem like the model's better than it actually is. It's negatives.
That statement may be true in some cases, but the answer here is very practical.
You don't want to fit the outliers.
I'm going to get to that in a minute, but that's not quite right.
I would say that even if you have a triangle that is a three-dimensional shape, you can always explain in a 2D, and this would be the minimal quantities to do a circle.
Okay, so that's out of manifold reason. Sorry, somebody said something, the right word. Who said that? Oh, okay, easy to implement. Yeah, sure, easy to implement. But there is something even more fundamental.
Easy to calculate.
Yeah, it is the only problem for which we know the exact solution. So many times in life, that is how we work. We like Gaussians a lot, also because they're easy to work with, right? So that's a fundamental reason. That's not what textbooks would say. But for no other norm can we write the exact solution and write those beautiful properties to those beautiful proofs. Anyway, maybe I should write that in the notes. But here is something interesting. So here is, this is straight regression, right? The same things you guys have been working on so far. I have some data points. I have a model. Then I use L1 minimization, L2. Which one's better? Sorry?
L2 seems
It's more robust.
Oh, I just thought it passes through more points.
Maybe L2 passes through. It just completely depends on something is good in the I norm. the I norm. Now see what has happened here. What has happened here?
L2 is affected by the outlier.
So there are two data points that are outliers, and immediately L2 wants to L2 treats all of the errors the same, and it really wants to go after that. So you end up, at least to the I norm or the S norm, sensible norm. This seems like a better fit, right? So the L1, so here you're basically saying AX minus the one norm is just the absolute difference, not the square of the absolute. What is this? So L1 is more robust to outliers. And why would that be?
You're not amplifying the distance
Yeah.
with the square.
Yeah, effectively. So what is least squares doing? Least squares is saying, let's say for the first point, y1 minus ax1. So this is what least squares is doing, right? Plus y2 minus ax2 squared plus y3 minus ax3 squared, etc., etc. Whereas L1 is y1 minus ax1 plus y2 minus ax2 plus. So obviously the larger the error, it will try to hijack the model. Okay? So that is why L1 can be better for outliers. And what's the question? Yeah.
I just raised my hand, but
It's automatic, like Martial always has a question, even if he doesn't have a question. Yeah, what?
if we scale everything down to less than 1, then wouldn't L2 be more robust?
It could be, but you generally tend to normalize these things.
So,
You're right. Different cases, you can have different kinds of behavior. But generally, you work with normalized data, which is a good reason to normalize your data. You take your data and normalize it between 0 and 1, and you work with it.
okay, so then L2 norm will be better.
Yeah. So this is the engineering of machine learning, right? You learn some theory and then you go in the field and then you normalize everything. That's one of the reasons. Good question. I like that level of granularity. But then you can be more, So then, again, the same thing. Yeah, you could do this. Okay, this is more, yeah. This is more general then, right? Like you can have, yeah. So you can have something like this, where you can have ax minus y in some norm, and then you can add some regularization. So that is one other way of being more robust. And there are many different kinds of regularizers that you can use, okay? All kinds of, regularization is like a pretty big field in itself. And when you regularize, then you're saying, okay, I roughly know that in this particular case, I roughly know that I want to be as close to the origin as possible. Or you can have x minus x naught, right? You're basically giving it some range. And the strength of this lambda will basically, change the, think of this as the prior, think of this as your likelihood. If lambda is large, then you have more confidence in your prior, or you have more confidence in where you want to constrain your solution to be. And again, there is some very interesting, like Sanjan was saying, if p equal to 2 and q equal to 2, and we assume Gaussians, this is the same as, Bayesian inference with Gaussian priors. In fact, if p equal to 2 and q equal to 1, that corresponds to what? I'm looking at the Gorodetsky students here. More pressure. There is something called a Laplace prior. It's not like Gaussian, it's more like this. So you can show that when p equal to 2, q equal to 1, this is precisely a Bayesian inference with a Gaussian likelihood and a Laplace prior around x equal to 0. So anyway, there are these equivalences. But what I wanted to conclude the class with is this, actually from another class I used to teach. And yeah, so here is a diagram I made some time ago. So this is, what this shows is, so minimizing ax minus y 2 plus lambda x 2. This is what happens, okay? So forget the circles. If you plot contours of ax minus y, the 2 norm of ax minus y, as a function of over x space, this is how it will look, right? It's going to look like a nice, what do you call that? Paraboloid. Yeah, if you cut it, these are all a bunch of ellipses. These are contours. So in 3D space, it's like a nice paraboloid. And this would be your least square solution. Wherever ax minus y has minimum value, that's